Welcome to our 13th lecture in mathematical finance. So we are currently talking about or discussing how to price European option in basically incomplete markets. So with the assumption that the option itself is not replicable. So there's no self-financing trading strategy which allows us to reproduce by trading in the market the payoff of the European option. And well, last time we stopped in the middle of the proof of Preposition 4.10. So let me briefly recall this proposition, and then we start where we left last time. So this is the proposition, so you can look it up in your notes. And the standard assumption we basically have now all the time is that we want to work with an arbitrage-free market, and we assume that it's a finite market as well. So this is a finite arbitrage-free market. So this is our assumption, which ensures that we have a realistic model of a real financial market. And now the statement of the proposition was, well, if the claim psi, so this is a random variable which is ft measurable and non-negative, is not replicable. Because I mean the case when it's replicable is, I mean, this is replicable, then it's, I mean, we completely discussed how to price and hedge these options. So this is what we care now about, is the case where this is not possible. And what we observed in this case is that there's actually a set of arbitrage-free prices. So the minimal, so it's not, it's an infimum, so it's not tended. So there's a lower bound of the arbitrage-free prices, and this lower bound is strictly less than the upper bound of the arbitrage-free prices. And this is what we're currently proving, is the set of arbitrage-free prices of the option psi is given by an open interval between these two numbers, so the infimum and the supremum. And then this is an open interval, basically tells you, well, if you assume that this inf or this sub here are the correct price, this will create an arbitrage on the market. So this is a really strict bounds. Okay. And then let us continue the proof. Continued. Where are we? Okay. So what we already have seen, and this was the first step in the proof, is that, well, the set of arbitrage-free prices by our duality representation based on martingale measures is an interval. So a convex set on the real line. And now we were in the middle of the second step, which was which were, okay, we are trying to verify that it's an open interval. So want to construct for, we have a price in our set pi omega. So we take an arbitrage-free price, which has this representation, and then we want to construct actually two probability measures. So two prices, plus, Q plus and Q minus, such that, I mean, these martingale measures, they're supposed to be equivalent martingale measures, and they're supposed to assign the option a strictly smaller and a strictly bigger price. Right? So this is the price under the martingale measure Q minus. This one should be strictly less than the given price P, and this would be again strictly less than the price assigned to the claim by the martingale measure Q plus. Okay. Right, so if we can find such two martingale measures, then we know, okay, for every price, arbitrage-free price, we can find a strictly smaller price and a strictly bigger price, which are also arbitrage-free prices. And this means then we have always a neighborhood around each point, ensuring that it's an open set. Okay. So what I want to do is I want to continue everything for these Q plus, and then Q minus works exactly the same, and you can look in the notes to check out the details. So we defined already last time, so just let me give you the definition. We defined the measure change. So we define the equivalent martingale measure Q plus by the radon-Nikodym density, which were called Z plus, and Z plus was, just to recall the definition here, defined by this construction of Z. So the Z was our, was coming from the separation theorem in Rn. So I'm not redoing the construction here. And well, one thing we needed to ensure is that this Z has a norm, so absolute value less than 1/3 for all omega. For all. We want to ensure that in the end we get an equivalent measure. So we need to ensure that this is a positive measure change. Okay. So this defines us in Q here. Suppose the martingale, equivalent martingale measure as well. Right? So Q will always denotes in some sense a martingale measure. All right. And what we have seen already last time is that this measure Q plus and the corresponding version of Q minus really fulfill this property here. So this here, the property here is always fulfilled. And now what's missing is, this is case to B. So we need to show, this is open, to show that Q plus defined by this radon-Nikodym density is indeed an equivalent martingale measure, which I already verbally said, but we haven't proved it yet. Okay. And I'm just doing it, so as I said, Q minus works analogously. Okay, so we have this measure, and the first thing, if we want to have we need to show that it is equivalent probability measure, right? This is, equivalent martingale measure means in particular you have an equivalent measure. So let us check that it's a probability measure. So if I take Q plus and, well, it's definitely a measure by definition or construction, but I mean, we need to ensure first that this whole set omega gets assigned the value 1 in order to have a normalized probability measure. So let us plug in the definition, which is, okay, we go from Q plus to Q, and then, okay, this is the first term. Then we have the second one. So this here leads to this, this goes here, and now this is missing term. So that's Q indicator function of omega, and then Q Z conditioned on the filtration at time t minus 1. Here we are. So this is just, well, applying the definition of the measure Q plus. Okay, and now let us do some calculation. Well, Q is a martingale measure, so the first one is definitely 1. This is nothing else than, right, this is the whole set, so almost surely this is the same as Z itself. That's good. And here what do? We can, again, drop the restriction to the whole set, because it's not a restriction at all. So we have this. Right? And that's good because right. Here's a minus, so here there has to be a minus, right? Since here's a minus, we have here minus. This means here's a minus, and now it works. So these two terms cancel, and indeed we have a probability measure. But now, second thing, we need to verify that it's an equivalent measure, but what we have here is that Z plus is strictly positive, and this is why we needed to have this assumption here that we normalize or Z to be less than 1/3 for all omega and omega. And this implies, so this here implies that Q plus is equivalent to the measure P. This is, you have seen it on one of the exercise sheets, I think 3, I guess 3, but if you want to check it in the notes, so my lecture notes, it's lemma B5, but as I said, you have already seen this on the problem sheets. Okay, so we have verified that it's indeed an equivalent measure, a probability measure. And now the last step is we want to show that it's a martingale measure. So it remains to show that Q plus is a martingale measure. So this means we want to show that the discounted price process under the measure Q plus is indeed a martingale. And what we have seen, so I mean, that there are different characterization of Q being a martingale measure. And what I want to do is I want to rely on the characterization based on trading strategy or gain processes. So let us take a self-financing trading strategy. And financing trading strategy. Peter Holfer. And I want to take it in a way where we start with an initial capital, which is, let's say, 0. And in the terminal time, I want to be non-negative. Okay. And now we have a characterization which tells me it's enough to check that the corresponding gain process has an expectation of 0 under Q plus. That's proposition 317, which tells me we need to show, and this is actually equivalent formulation, so this is really, we lose here nothing. We really need to show this. I mean that under the measure Q plus, the corresponding gain process corresponding to this trading strategy as the expected value 0. Okay. Okay. Okay, this is a bit more work. So let us start with the first observation. And the first observation is that, well, the expected value under Q plus of GT, so the gain process at the terminal time, is definitely non-negative. Since we have here a almost sure positive random. So under the measure Q, this is almost surely positive, as Q plus is already shown to be equivalent to Q, and this is equivalent to P. So we have by assumption that this is a non-negative random variable, so the conditional expectation has to be non-negative as well. Okay. Okay, so what we need to show is means to show that expected value under this measure Q plus of the gain process is also non-negative, right? We have seen that it has to be it's non-positive, right? So we have shown that it's non-negative. So if it's non-positive as well, then it's equal to 0. Okay. Then let us start our calculation. So we want to show that this here is non-positive. Wait. First thing is we plug in the definition of Q plus. Okay. Right. I should use more than one color if I have. Okay, this is, and now we have here plus Q phi Z, and minus g and time t of phi, and then we have here the conditional expectation on the q of z condition to t minus 1. Right. Okay, now we know that this here is equal to 0 as q is a current martingale measure. Okay. That's good. And well, let's see what we have here. So if you put this together, we have g at time t of phi, and then we make a bracket here. So we have z and minus conditional expectation of z constrained to the filtration at time t minus 1. Okay. Right. Let's keep calculating it. So now we do our usual trick, which is the tower property. Which tells us we can sneak in another conditional expectation with respect to Q. Right. And that's my copy pasting what we have before. Now we constrain everything to the filtration at time t. And here we have the freedom to constrain to whatever we want to. And the filtration at time t is the smart choice because z is ft measurable. And well, the conditional expectation of that with respect to ft minus 1 is ft minus 1 measurable. So in particular, ft measurable. So what we see here is we can pull it in, and then we have the conditional expectation of gt, so of the gain process, the terminal time of phi. So we use here now the martingale property of g, so gt. Gt phi is martingale. So this brings us to this. And well, this is our measurable, so we keep it like it is. Okay. Right, sorry, that's here are some brackets missing. Right. Oh, I pulled it. This was the whole purpose, to pull it in. Now let me count the brackets. That's okay. That's okay. Perfect. Okay. Cool. And now let us split up this term into a part which is, and so we consider the gain process at time t minus 1 now. And split it up. So the gain process is now decomposed into the part, so the gains up to time t minus 1, and then the gains we make in the t grading period. So that's what happens here. And well, so this is minus plus right? The gains we make in the teeth trading period. Okay. So that's this is not really hard. Okay. All right. Okay. And now we want to understand why these two sums are non-positive. So that's here, let's call it 1 and this 2. And now let's consider 1. So white. Okay, so let's come back to 1, which is this here. Okay. Right. So what is this? We do our standard trick, and now we sneak in the conditional expectation of all this here with respect to the filtration now at time t minus 1. Here we are. And this is rather nice. Because now, well, this term here is, okay, this term here is ft minus 1 measurable. This one is ft minus 1 measurable. Measurable. So if we pull in now the conditional filtration, so we have here z conditioned on the filtration of t minus 1 minus z condition on the filtration of t minus 1. So this goes to 0. And then we have that this is the product of something with 0 is 0. All right. And now let's come to the second sum. Okay. And let's try to understand why this is also non-positive. So let's copy what we have here. So we want to understand why this here is non-positive. Well, what is this? So let us multiply this out. So this is the gains from the teeth trading period multiplied with Z and minus the gains from the teeth trading period multiplied with the conditional expectation under Q of Z constrained to t minus 1. All right. All right. So what is this? So this here is nice. This is equal to 0. as this gains here is by construction of Z in the, so these gains are orthogonal to Z. And here we are. Okay, so this is 0. So let's go back to the second term. So we have here minus, and now we do our same trick the third time. So we sneak in the conditional expectation with respect to t minus 1. Multiplied with and well, this is 0. Oh, sorry. It's not equal to 0, it's less than 0. All right. And this means right, this is, the definition of K, T. Okay, here we are. So that's again 0, because let me give you the explanation again. Right, this is equal to 0 as well. We can pull in the conditional expectation. This here is ft minus 1 measurable. This here is ft minus 1 measurable. And this means, since Q is a martingale measure, the expected value of the gains, of the discounted price movements are 0. Okay. So combining all these calculations, we see that Q plus assign the gains processes the expectation of 0, and therefore Q is a martingale measure. All right. And this completes our proof, which we started last time. So the measures we constructed, Q plus and Q minus, are indeed equivalent martingale measures doing the job we wanted them to do. And you can do Q minus with exactly the same calculations. So I dropped them here. But if you want to practice, go through them, do the same calculation for Q minus. So let me give you one immediate corollary now, this theory of preposition, and then discuss an example. So the first corollary is which tells you, well, if we have a claim, and this is our goal, we want to price and hedge European claims. And well, what we now know is that this claim is replicable if and only if the set of arbitrage-free prices is 1. Yeah. So this is the cardinality. No, this is a standard notation for the cardinality of a set. Of the set this works for everything. So, so we know that the set of arbitrage-free prices is exactly one element. So there's a unique arbitrage-free price if and only if the option is replicable. So last time we already have seen the one direction. So if we have a replicable claim, then the set of arbitrage-free prices consists only of one element. And today now, by the, well, already last time a bit, by proposition 4.10 here in green again, means, well, if there's, I mean, if the set consists of one element, so then the claim has to be replicable, because otherwise the set of arbitrage-free prices would be in true open interval. So the only chance you have, if you have only one arbitrage-free price, then the claim has to be replicable. So this is, there's nothing to prove. This follows from the last, the proposition we have proven this time and last time. All right, then let's come to an example. Which is, now strictly speaking, not an example, it's more a discussion. Namely, let's apply what we have learned now to European call option. Okay, so right, we want to assume that we have an is a finite and arbitrage free market. And that's the usual setting, and we want to consider a European call option. Right, that's with maturity T, strike price K, and that's the okay, and so this is the European call option, European call option. Right, and let me make the assumption that this is the usual, I mean, standard assumption of a risk-free bond, namely that there's an interest rate, and the interest rate describes the growth over each period of the risk-free asset. So that's, and we want to that the interest rate here is non-negative to make our calculations easier. Right. All right. So if I take now, and if we want to consider now the set of arbitrage-free prices, I mean, this is what we are studying here. So let us take martingale measures, and we know by the first fundamental theorem asset pricing they exist, the martingale measure. So, and this might be a convex set, as we have learned. So we take an arbitrage-free measure, then we know that this leads to a price. So call price So this is an element in the set of arbitrage-free prices of this call option is given by the conditional expectation, the condition to time 0. So here just the expectation of the discounted claim with respect to this measure Q. Right, and well, so this means the price, or one price, so one arbitrage-free price, there might be more than one, is given by this neat formula. Okay. And now let us try to figure out a lower bound for the price of the call option. Right, so you take your call option and then you right? And now you apply Jensen's inequality. Jensen's inequality, right? Which allows you to pull out here this convex function. So you have now the positive part around this expectation. So we have here the discounted price at the terminal time minus k divided by the discounting factor bt. But now the discounted price processes a martingale. So what we know is that this is nothing else than a 0. And well, this is our two constant, and this is here bigger than 1. This is why I assumed the non-negative interest rate. So what you have here is the call option. Would it be like immediately paid off, right? So what we see here, the call price, every call price. So these are my call prices. Is bigger or equal than what's called the intrinsic value. Value, which is the payoff you would get if the maturity is now. So what you see is, this is the price, the current price you observe from the market. So this is something you immediately see on the market. Because you know the current prices and, well, you know the strike price. And this means this gives you a lower bound of every arbitrage-free call price. It doesn't matter which martingale measure you pick here, because the right-hand side is independent of Q. So it has to be bigger than this intrinsic value. The difference is basically the time value, because I mean, for European call option, this is a non-negative value of the call price, which might change over time. Okay. So you see here, you get an immediately lower bound of call prices on the market. All right. And we will come back to the discussion of European call options and put options later on. If we discuss also American versions of it, we will also discuss the European one again. All right, but for now, let us come to the next chapter, which is the characterization of completeness. So this is section 4.2. of right. So okay, first let us recall. So what was completeness? So market was called complete. If every claim is replicable, right? Because this were actually the nice situation under which we can price and hedge all the European claims. So this was actually the markets we really like because they make our life rather simple. So is called complete if every claim is replicable. Okay, so that's okay. So this is, and now, I mean, what we have seen that, for example, in the binomial model with one trading period, this is actually the case, right? So every European option, we realized we make our approach to replicate it, and this worked. So basically, we got a pricing formula and the replicating strategy for every European option. And well, since we learned a lot already from the binomial model with one trading period, we want to understand now, okay, how can we, I mean, see whether a market is arbitrage free and complete. And we want to understand this in terms of martingale measures. I mean, this is at least the first step. And this brings us to the second fundamental theorem of asset pricing, which exactly characterizes the completeness of a market in terms of martingale measures. So this is the second fundamental theorem of asset pricing. Okay. So what we want to assume is, and this is our standard assumption, of course, which we have already an arbitrage-free market, because we have understood when a market is arbitrage-free, and this makes it a realistic model. So we take, to make our mathematical life a bit easier, we take a finite market, finite and arbitrage-free market. Right. Okay. So this is the assumption. And now the statement of the theorem is that this market is complete if and only if the set of martingale measures consists exactly of one element. And this is another rather deep inside, but for us it will be now rather simple to prove, because, well, we did already the hard work in the last subsection. And if you want to, you could use the techniques we developed there to directly prove the fundamental theorem of asset pricing, the second one, without this detour about incomplete markets. But let me first give you one remark, which is a informal one, so no number. Here we go. So second fundamental theorem of asset pricing holds without the restriction to finite sample spaces. Right. So this is, I mean, we do it here again all for finite spaces as we have done in the last sections to avoid the use of abstract functional analysis. But just for you that you keep in mind, even on a general probability space, this theorem is exactly the same. All right. So now I promise you the proof is actually rather short for us because we did already all the work. In particular, in the longer, the proof with the longer proposition we just finished at the beginning of the lecture. So why is this now simple? So first, let me show you that if the market is complete, then we have exactly one martingale measure. Right, so assume yes is arbitrary and of course finite, right? But yeah, that's not the point here. So first of all, we know that the set of martingale measures is non-empty. There you see why we need finite space, because finite probability spaces, because well, this is how we prove it. So this is true by the first fundamental theorem of asset pricing. Okay. Now the question is, why is there only one element? So take Q1 and Q2 out of this set. Well, this is possible if it's a non-empty set, so we take two elements and we want to show that they're the same. And now if we want to have a financial argument, if we consider the claim of an indicator function of A, right? This is a non-negative random variable, so it's a claim, and it's even a replicable claim because we have complete market. So this is a claim for every set A in F, since this market here is complete. So because every claim is replicable, so this one in particular. Complete. Right. Okay, that's good. Okay. So how can we use this now? So this means if we have a replicable claim, the price is unique. And this was lemma 46, right? So if we have a replicable claim, we already know the price is unique. Unique. Price of is unique. This means if one calculates the probability of A under Q1, well, this is nothing else than the expectation of the indicator function of A under Q1. Well, this is, as we learned, the price of the claim indicator function of A. But this, since the price is unique, is the same as if I take, calculate the price on the other equivalent martingale measure Q2, and this is nothing else than, well, the probability under Q2. And this holds actually for all A with the same argument. Okay, and well, this means if two probability measures are the same for all A, well, in the sigma algebra F, this means they're the same. Okay. So uniqueness is actually easy. And the other direction is easy as well, because we did all the work already. Right. So if the cardinality of the set of equivalent martingale measures is 1, then so if I take on claim, okay, and let psi be a claim, then we know that the price of psi is unique, right? Because there's only one martingale measure, and we can use the one martingale measure to calculate the price. And this means psi is replicable. Why? What is our last corollary? This is 411. Right? So this is the corollary we have here, telling me, well, if the price is unique, then the claim is replicable. Okay. All right. So that's finished the proof of the second fundamental theorem in asset pricing. All right. But let me also give you a second characterization of completeness of a market in terms of martingales. And this is actually a discrete version of the martingale representation theorem, which tells us here that we can represent every martingale with respect to a discrete characteristic integral. This brings us this is proposition. Position 414, which tells me, okay, let us consider a finite arbitrage-free market. I just recall it, and here the assets is the finite and arbitrage-free market. Arbitrage-free market. These are standard assumptions. Right. And we take a martingale measure, which exists by the first fundamental theorem asset price. And then we have the following equivalent characterization. Equivalent conditions. So the first one is actually that this martingale measure is unique. So the set of martingale measures consists only of this measure Q. And this is, as we know, by the second fundamental theorem, asset pricing, equivalent to completeness. And the second condition is, well, for every martingale under Q, so Gale under Q, let's call it M, we know that there exists an RD valued predictable process. So right, this corresponds to the positions in the D risky assets such that the martingale can be represented as the initial value of it plus the discounted gains. Right, so we take our positions in the market and then we trade into the discounted price process for okay. Right, so the statement is there exists exactly one equivalent martingale measure if and only if all martingales can be represented as discounted price, discounted gain processes. Okay. Cool. Of course, I mean this requires some proof. So okay, first direction first. So let us take a. I mean, so what we want to assume if there's a unique, I mean, if there's a unique martingale measure, so the market is complete, then we can represent every martingale with respect to such a discrete stochastic integral. So what we do is we take a martingale and we assume it's martingale under measure Q. So under the equivalent martingale measure Q. And now we want to show that it can be represented as claimed with respect to such discrete stochastic integral. First thing we do is we decompose it into a positive and a negative part. And so the martingale at the terminal at time t, as every random variable, can decompose into a positive part minus its negative part. And now you wonder, why do I want to do it? Well, because if I want to have I mean, these are two now, the positive part and the negative part are contingent claims. And this is the point here. Plus and minus claims. So non-negative random variables, which are FT measurable. And now second fundamental theorem of asset pricing allows us to replicate every condition claim. And what I want to do is I need to take care of the discounting factors. So I multiply them with BT, there are claims as well. This is just because of the discounting. So now by the second fundamental theorem of asset pricing, we can replicate these two claims. So there exists a trading strategy phi plus consisting of beta plus and alpha plus, and the same for minus. Which are self-financing trading strategies. Self-financing. Such that MT so this here corresponds is reproduced by the trading strategy phi plus, and the negative part is reproduced or replicated by phi minus. Okay. Okay. And well, now I want to use, I know since the trading strategies are self-financing, I can represent the value processes associated to these two trading strategies in terms of a discrete stochastic integral. So plus and minus self-financing. We know that let me get rid of the discounting factor here. So let's move to the discounted objects. So this one can be represented at the initial capital I need for this trading strategy phi plus the gains, the discounted gains I make up to time t. Right? ST delta CK. And this same is true for the negative part. Oh, that's P plus. So this is P minus. And then I have here the same with the minus, and here the same with the minus. Okay. All right, that's good. Okay, now I need just to put them, to these statements together. These. So okay. So let us recombine it. So first, I wanted to have these representation with respect to every t, so I need to note that these here are martingales under Q. So that's a martingale as well. Are martingales is under Q. So what does it brings us? Well, if we want now to understand or find the representation of MT, well, as this is a martingale under Q, this is the same as taking the conditional expectation of M at terminal time T with respect to Q, and then condition everything on the filtration uptime to time t. So that's okay, and now we use our decomposition into the negative and the positive part. Right. And well, then we will have here our presentation formulas. So this is, there are martingales again. So we have here minus the filtration. Right? So this is the martingale property of the discounted value processes with respect to phi plus and phi minus. And now we put in the self-financing condition. This is the initial capital for phi plus, and this is the initial capital for phi minus. And well, these discrete, these sums are linear. So I have here minus. Right. And yeah. Okay. And here we are. So what do we do now? So this is now our AK, right? So what we see here is this martingale M. Where's my? So this martingale at time t can be represented as a constant. So the initial capitals for phi plus and phi minus plus discrete stress integral with respect to a predictable dimensional stochastic process. Right? And this is, we briefly recall our condition 2i's. This is exactly what we wanted to show. Okay, so let us now prove the reverse direction. So what we want to show is that if we can represent, back again, so if we can represent every martingale under Q in terms of a predictable process invested in the discounted risky assets, then the market is complete. So there exists exactly one martingale measure. Okay. So let us show that the martingale measure Q is unique. So as we take a event from the ZF, so from a sigma algebra, and Q is our martingale measure, which is assumed to be equivalent. Okay. So now let us, consider the martingale. So define the following martingale. MT T by you take your the conditional expectation with respect to this martingale measure of the following claim. So you discount with respect to the risk-free asset, and then you consider the claim to indicate a function of A. Right? This is the same trick as we have done now several times. So T and T. Well, MT is a martingale, well, by construction, right? So you, this is what we called at the beginning Levy's martingale. So this is the simplest example of a martingale we have seen. So since MT is a martingale under Q, We know there exists a d-valued predictable process alpha t such that we can represent this martingale, and in particular the terminal time, with respect to, and let me directly discount everything to save a bit of time. So we represent it as a discrete stochastic integral of this with respect to the discounted price process. Right. Okay. Okay. So what does this mean? This means that we can replicate the claim of the indicator function of A. Because this here is just the discounted claim, so let me here. So if you look at m at the terminal time, this is just this. All right. So we can replicate the claim, and the good news here is, well, why can we do it? Because we have only defined the risk key positions. So by enhancing these risky positions, to a self-financing trading strategy. Well, this is what we know we can always do. If we have only defined the D position in the risky assets, then we can always enhance it by choosing the right position in the risk-free asset to a self-financing trading strategy. Okay. Such that phi such that mt is equal to phi. And now we know, this was what we have done in this lemma, that actually the price for every replicable claim is unique. So if we have the replicable claim, you know, that this is, I mean, it's the same for all. Same. So this was, as I said, the uniqueness of prices of replicable claims for all. Right. And if this is the case, this means, well, every martingale measure assigns all set in the sigma algebra the same value. So there exists only one. Oh. Okay. 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 Just one warning, because this is a common mistake easily made in, for example, an exam, is not every model, and I mean, we have seen already several examples, so not every model is complete. Right? I mean, so if you look at the binomial model, and this is the model we are studying most, I mean, this is a complete market, which makes our life very nice. But then some students get the impression that, oh, I can always assume that the market is complete. No, this is an extra assumption which needs to be verified. Right. So this is just keep it in mind. I mean, of course, most examples we're considering are complete market because we can do nice. I mean, our calculations are very nice, but this is, I mean, check when you're allowed to do this. To assume that there's only one martingale measure. Sorry, no, market is complete. All right. I mean, so this said, let us consider a complete market. Namely, let us come back to, come back to the binomial model, and now let us consider it in several trading period. So this is, so the nice thing about the binomial model is that you can calculate everything explicitly. And this, I mean, if you want to do numerical approximations, this is super nice to work with. Okay, so this is the model I want to consider. All right. Okay. So what do we want? So the several trading periods means consider the let us set up the binomial. So let me once define it, in the future, if I talk about the binomial model with several trading steps, this is the model. So this is, we have our risk-free and one. So one, we consider it only for one risky asset, but I mean, the extension to de-risky assets is pretty straightforward. Where T is now really set, assume going from 0 to T. So we have T trading periods. First thing we need to do is we need to define the underlying probability space. So what is our probability space? The probability space omega f p by so we choose omega to be the product of u and d's. So that's the whole omega, which consists of a vector in t dimensions, and we assume that each of these vector either takes the value, so each component is either u or d. So that's the filtration. I mean, since we have here finite probability space, well, that's very simple. So we take the power set, and we want to take a probability measure. The physical measure P should be set up in a way that each element gets assigned a strictly positive value. So this means each element in our set omega, so it can really appear. Okay. Yeah. And well, what is our U and D? So U and D are some positive real numbers. So, and I mean, D stands for downwards movement, U for upwards movement. So, so let's assume D is smaller than U. Okay. And now on this probability space, we introduce, so we want to define the price movements of the risky asset. So we need somehow random variables. So we consider the independent random variables, right? This is so this is, right, for each time we need to have one, and we define them by, well, at time 0 we assume that there's no randomness, so that's just for convenient. We set the zeroth random variable to be 1, and then the random variable at time t. So the tth one is just the coordinate process. So we project to the tth entrance of our in our set, right? So this is for t without 0. Okay. No. So they're independent. I mean, and now what's our model? So the risky asset S T is just given by, well, the product. So we start at time 0, we have the price at 0, which is a constant. And then we move up or down. So this is the product from 0 to t of y for t and t. And S0 is a positive constant. Right, so this is here our market. Oh, right. Okay. And okay, this is our risky asset. And now we have also risk free asset, which, so the risk free asset B T is, well, I mean, there's no, this we need no probability space. So this is just our idea of an interest rate modeling the returns in each trading period. So this is the interest rate R is assumed to be bigger than -1. Okay. Well, this is our price movements. And well, was our filtration to complete? We always wanted to work on a filter probability space. So here the filtration is, as usual, so FT is given by the filtration generated by the prices up to time t. And note at time 0 we have constants, so we have the trivial sigma algebra, and at the terminal time, well, all events are revealed, so the sigma algebra at time t is equal to the underlying sigma algebra f. So this is all this assumption we always wanted to have are fulfilled. Okay. Wait. Right. Okay. So this is our model, and next time we need to start with what we have to do always first, namely we start by showing that under suitable assumption on the parameters u, d, and r, the binomial model is indeed arbitrage free. Right? This is the first step we always need to do before we can talk about pricing and hedging of risky assets. And now we have also the tools available to show that the binomial model is actually a complete market in general. Of course, again, assuming that they have the right assumption on the parameters. So this is what we do. Next time we start showing that the binomial model is a complete and arbitrage-free market, and then we briefly talk about pricing and hedging of European options before we go on to talk about American option as well. All right, thank you very much for watching the video, and well,